Ladies and gentlemen, hello and welcome back once again to the briefing room. Yes, indeed, my name is Eric Cavanaugh. I will be your host for our event today, and what a fascinating topic, folks, especially in light of world events. The world is captivated right now trying to track down a certain individual who did some interesting things, and we're going to talk about that perhaps at least in the abstract today, because the topic is connecting the dots, how a graph database enables discovery. And folks, I am particularly interested in this topic because we have dealt with all different kinds of databases in some of the research that we've done and in various briefing room months over the past 3.5 years or so, but we've never done a deep dive on graph database technology, so that is what we're going to do today. So there is a slide about yours truly and enough about me. So as many of you now know, the whole mission here in the briefing room is to reveal the essential characteristics of enterprise technologies. You in the audience play a significant role in that process, so please don't be shy. We always get great questions from the audience, very detailed questions, and that helps us keep on track and reveal the kinds of details that you need to make decisions out there, especially if you're gearing up to make a purchase of some kind. So please reach out, give your comments. If you tweet, use a hashtag of BriefR, and we'll be sure to comment on what you send us via Twitter. So this is, well, actually cloud is next month in the high performance analytics, and June, of course, is database month. So we've talked about a couple different databases already, and like I said, today we're going to talk about the graph database. Well, it's actually not a new thing. For some of you who have been around for a while, graph databases have been around for decades, and they were designed originally to focus on helping identify relationships and then be able to traverse the information in the database to identify those relationships and figure out what they mean. So certainly we hear a lot about this kind of thing in social networking. If you look at some of the social graphs that have been created to identify key influencers, for example, on Facebook or Twitter or LinkedIn or other places like that, and also, of course, in the whole world of national security, trying to track down the bad guys. Who are they? Who are they related to? You see a lot of information coming out of telecom industries, for example, of who called whom at what time and what length and duration and who else did those people call. And if you try to solve a problem like that with a relational database, you're going to spend a whole lot of time and effort, and you're probably going to wind up pretty unsatisfied with the results that you get because they're really not designed for that kind of processing. So we're going to dig deep today, and I got to tell you, I'm going to put my thinking cap on because as much as I've researched it so far, I still don't have a completely good understanding of how this works. So I'm very keen to figure that out today. Robin, of course, is our analyst for today, chief analyst here at the Bloor Group, one of the most well-known and well-studied database experts in the world. Very pleased to have him online, and very pleased to have Objectivity in the briefing room today. So they develop NoSQL platforms. Its flagship product is Objectivity DB, but it also has InfiniteGraph. So we're going to hear a lot about that today, and they have a new product or a new project coming out called Graph My Life, which is a mobile application that provides search capabilities across social networks. And folks, I have to tell you, I'm dying to watch how that pans out, because those of you who are out there in the world of trying to get a single view of the customer, for example, well, I think there are going to be some new ways to solve that. And we're going to hear from Leon Guzenda today. He's one of the founding members of Objectivity and one of the original architects of the Objectivity database. And Leon is a really, really sharp guy with a lot of experience in the industry. So his chops go way back, and they are deep. And with that, I'm going to pass the keys of the WebEx over to you, Leon, and just click anywhere on that slide and use the down arrow on your keyboard, and the floor is yours.
Thanks very much, Eric. Okay, it's a pleasure to be here this afternoon. So let's try and move forward here. And everything's working apart from moving forward.
Yeah, just click on that, click on the slide and use the down arrow on your keyboard is the best way. There you go.
Okay, yeah, so we've been around a couple of decades. We were NoSQL from the start because we were object-oriented. We built our first petabyte database in 1999 and were able to publicly talk about another one in 2000. So we've been doing petabytes for over a decade. And as Eric said, we have the three products. Today I'm going to primarily focus on InfiniteGraph, which is built on top of Objectivity DB. And I'll also say a little bit about Graph My Life, which is built on top of InfiniteGraph. Our customers typically have been in the process control and telecom equipment space, the DoD, the Department of Energy, and the intelligence community. So we've been involved in systems like this, which is a knowledge base of human intelligence deployed out by, in this case, by the DoD. And don't worry if it's looking a little bit fuzzy. It's fuzzy because it was real data. But they build systems that allow the analysts to track people and find problems and cope with them. Now, in a typical big data analytics setup, you'll all be familiar with this kind of picture, structured, unstructured, semi-structured data. These days, increasingly using clusters of commodity Linux boxes, though this might equally well be a specialized analytics box or an Oracle big data store or an Exa store or something. And then with the all-important aggregation and analytics up at the top there with visualization to make sense of it all. And so we've talked about the NoSQL technologies. I don't need to dive too deep here in this audience, but we have the key value stores and the document stores, the big column clones. And then there were the object databases, which focused not just on the objects and on inheritance in the objects, but on the connections between the objects. That was the big differentiating feature. And we've refined that now into the graph database, which is really just has two object classes. So vertices are nodes, maybe a city would be an example, and edges are the connections between them, with data in the edges generally. So that might be roadways, flight paths, waterways, railroads, that kind of stuff. It turns out that these other NoSQL technologies, and in fact, as you'll see, relational technology isn't very good at handling relationships. The more interconnected things are, the more it's time to start looking at a graph database. So we came to this conclusion some while ago that almost all of the analytics going on out there was really statistical. It was statistical correlation. I tried changing the annual percentage rate on a credit card for medical transactions. I wait 6 months, I analyze the results and see if that helped my bottom line or not. You know, maybe I'll try it on some other kind of transaction. What you're really doing there is statistical correlation between a couple of columns in one or more tables. And if you look at almost all the business intelligence applications out there and software out there, it's doing that kind of thing in one way or another. Sometimes very specialized for a particular vertical, or it can be general purpose, like the R suite of tools. But we were strong in the relationship world and looking at large networks of related objects, large trees. And so we decided that there was value in looking deeper into the connections and finding the extra value in those connections. If you look at a very simple database, here's a simple relational database, you know, with 6 or 7 tables. And if I want to find whether there are any connections between a row in the left-hand table and a row in the right-hand table, that's a pretty nasty SQL query to write. You have to know the type and name of every column. You have to write extremely extensive join statements, and it's going to run for a very long time. I'll show you an example later of a system that was built using one of the major relational databases, and which was taking hours to days to perform. And I'll show you a demonstration of it that normally takes seconds to minutes. The reason for that is all the objects that represent the nodes and the connections between them have unique identities, and so we can look them up extremely quickly. We can use them like pointers, so we can traverse networks of objects very, very rapidly. In fact, in the first release of our product back in 1990, we didn't even have a query language. You found an object, you know, 747, and then you traversed to the wings, to the engine, to the parts of the engine, and so on. And everything was done visually on the screen. So you weren't actually making any queries at all. You were just poking on bits of the picture on the screen, which in the database was traversing relationships. And that's what we've exploited in InfiniteGraph, the ability to maintain huge networks of relationships and traverse them very quickly, particularly when you want to find connections between particular objects. Whereas our main product for years was used in very specialized industries like telecom equipment, process control equipment, and the intelligence community and so on, InfiniteGraph's seeing application all over the place. Market analysis, the little picture there, you can't read it all, but those are all the consumer product companies, the biggest consumer product companies in the US. And you see they're all owned by about 7 or 8 major conglomerates. Social network analysis, very important in things to do with the web, all these nice social apps that we like, and of course in the security community, the intelligence community, and things like customer relationship management. They all are dealing with graphs inherently. Logistics, seed to a consumer. What was it that made little Johnny sick? I'm not sure if you heard about the problem that Tylenol had just a couple of years ago. This is not the famous case from a few decades ago. They were having medication turn up on the shelves that smelt bad when you open the package. Turned out there was nothing wrong with the medication, and they knew everything about the ingredients and the manufacturing process and how it got into the pharmacy and everything else, but they still didn't know why it smelt bad. Well, when they tracked back and actually walked back through the chain of events, they found at one point where the product was sitting on wooden pallets, and the wooden pallets had mold on it. And the mold got onto the packaging, and then it grew inside the plastic packaging, and that's what produced the nasty smell when you open the packaging. They had all the RFID tag tracking. In their database, they had all the information about the nodes, and they thought they had all the information about the connections between the nodes, but they actually didn't. They were missing the key piece of information that was actually in the connection and not in the nodes themselves. And then there are other problems in healthcare informatics. We should have a quite major announcement in this area soon, where there are things like checking ingredient and drug and allergy interactions, treatments, locations, who you've been close to, were you on the airplane with someone who had something nasty. And we've taken the National Drug Code database and loaded it into InfiniteGraph. And you can play with that as a demonstration up on our website. There's also the Internet Movie Database, by the way, and then another one I'm just going to give you a snapshot of in a while. So let's see it for real. Let's find some value in this. So here's a simple database. Those are all the rows in it. There are 3 tables, or it could be 3 databases. Doesn't really matter. There's something going on here, and actually we need to know about it as soon as we can. Now, I look at this, and it takes me quite a long time to figure out exactly what's going on here. And it's not that complicated. So let's take all that information and load the nodes. Let's take the situations and people and put them in nodes, and then take the connections, A called P, P called Q, and so on, and put them into edges. So we now have nodes and connections. I still can't see really what's going on. Remember, we're just loading them into vertices and edges in InfiniteGraph. And here they are. So the light blue ones are vertices, the orange ones are edges. And I'm beginning to see something. Now, let's imagine that I'm an analyst, and I have one key piece of information, and that is I know something about combatant A, the person in the top center there, because we saw this person near to something bad, or maybe we caught this person near something bad. So we know that. Now let's look at the other connections, and suddenly a picture has emerged. See the red lines there? What we're looking at is a bunch of people who are now suspects. And target T, if it wasn't already well protected, needs protection, or it needs extra protection. We have to be extremely vigilant, particularly in looking for any of these 5 people being close to this place. So what's happened here is that we've turned the tabular information, which wasn't easy to digest and see a pattern in, into something that the eye can quickly turn into useful information. And we've diagnosed the situation. We can now do something about it. Very simple demonstration. A key here is that we split the data that came from other places, constructed the graph, the nodes and the edges, the connections, and then we were able to put up a visualization that helped us find extra value. It might have been that we were doing this over and over and over, looking for patterns like this, looking in customer records or whatever, doing this with machine algorithms. But most times we find that it helps to use visual analytics, where you put the right kind of picture up on the screen, so that the people who need to examine the information can make sense of it quickly. And we work with a whole number of different people on this, but companies like Tom Sawyer, Cambridge Intelligence. It really depends on the use of that data, the vertical domain. If we were doing something that was electronic chip oriented, then we'd probably just be using a straight ECAD tool and using some of its visualizations. So there's a lot of work still to be done in the visual analytics area. We're part of the National Visual Analytics Consortium that's funded by the Department of Homeland Security, and they're continually trying to find better ways of allowing people to interact with the data. And that's partly about the graphic aspect of it. It's partly about display technology, and now it's getting into areas like haptics, where you literally touch your way around a database looking for irregularities, or you get audio or visual signals of things going on in particular parts of a very, very large data set. So we're just scraping the surface really at the moment in visual analytics. A lot of those things don't scale very well. Graphs can scale extremely quickly. Amazon S3 reached 2 trillion rows a month or two back, I believe. But we've got sites where they're processing tens of trillions of new objects per day, with 1,000 or so analysts throwing really complex queries at the system to try and get answers that will help them with the cases that they're working on. And if you look at the fan out, if everything was regular and every node had 10 connections to other nodes and each of those did and so on, at 6 degrees of freedom, the 6 degrees Kevin Bacon, if you like, you may have to traverse a million nodes a million links at worst to look at that information and find what you want. And it goes up very rapidly. So at 9 degrees, you're up to a billion. 15 degrees, you're up to a quadrillion. Imagine doing a quadrillion individual join operations on a, even an extremely large relational database engine. It's going to take some time. And I can tell you that we're involved in systems that go out 18 or 20 degrees of freedom because they've got so many different kinds of data out there. By the way, it's not really 6 connections to anyone else in the world. It's 8 or 9 these days because the population's exploded since someone came up with the number 6. So we see ourselves in InfiniteGraph as being not a replacement for these other data repositories, for the IT, the enterprise databases, or your brand new, shiny, big data setup. We're not in there to replace that. We want to extract useful information from it, the graph information, and allow you to store it and manipulate it extremely rapidly and very safely. So InfiniteGraph is distributed database engine, distributed graph database. It's very scalable. We've proven that we can do petabytes and tens of trillions of nodes and so on. We can run queries in parallel because the underlying engine supports that. And we spend a lot of time making it possible to plug in your own algorithms and your own visualizers and so on. So it's a very simple thing to download InfiniteGraph, load data into it from whatever source you have, and start using it and finding out useful stuff. Generally, people want to build proofs of concept that have a billion nodes or more in them. There are definitely open source products out there that people experiment with, and they're fine as long as you don't have graphs that are too large or don't have to be distributed. If you can't tolerate a single point of failure and so on, then you really need to look at an industrial strength product. some of the things you can do. So we've loaded the data into the graph database. Well, we can start somewhere and navigate somewhere else. Start here, and let's explore out of San Jose and go down all the roads and find out where we get to. You can include or exclude kinds of nodes or kinds of connections. So let's say I want to move an extremely large load from here to New York, and it's too wide to go on a railroad track, and it's too heavy to go on the road. My only choice really is waterways. So I can just say, well, let's just look at waterways. Or I can tell it other things like, don't go south of this latitude in the summer or north of this latitude in the winter. You can express that much faster in a Java query than I can say it. Then you've got the parlor trick, if you like, find the connections between things. It's a single line of code. Give it two objects, we'll find the shortest path or all paths between those two objects. And as I said, you can plug in visualizers. So in that logistics query, I could compute the cost to get to a particular city every time I change the mode of transportation. Let's say I could take it by road and rail. Every time I switch over, I want to calculate how much it's cost to get to this point and how long it's probably taken to get there. And then I might put up different visualizers. I don't want to visualize every link that's traversed because it runs at millions per second. So I probably just want to know when the first viable path is up there, and I want to see that on a map, and I want to see the cost. And then I also want another visualization, another window, another pane, that shows me all the alternatives and what they look like and where they went and how much they cost and how long it would take to do it. I might opt to spend a little less money and get there a day later or whatever. So those things are, these things can run in parallel. As I said, we can do the queries in parallel. We can also load data in parallel. So it's very easy to take data from an external source, maybe that's been processed, munged through a Hadoop setup with MapReduce to produce load files that then get loaded into the graph database. And they can be loaded in parallel to get you started quickly. There are lots and lots of graph algorithms. Now, graph theory has been around for 300 years. It's only taken 300 years to get a database that works with it really well. But things like connectedness, I've noticed, the degree of a node, that's how important are you in a social network. How many things point to you? How many things do you point at? My guess is that Eric follows fewer people in the industry than people who follow him. The same for Robin. And then the span of the graph can be important for some algorithms. So how far is it? What's the maximum number of hops I'm going to have to take to get from one side of the graph to the other? So these are all algorithms. We supply some of these out of the box with InfiniteGraph, and we're providing samples for many more of them. We're actually working on a benchmark with one of the West Coast universities to set up a little framework that you can use any of these algorithms with more quickly. As I said, you fit InfiniteGraph alongside something else, unless it's objectivity, in which case they can coexist, but you might have an Oracle Big Data solution. The little demonstration I'm going to point you at in a moment, first of all ran just in a I think it was a MacBook, and then we hooked it up for Oracle Open World last year so that all the data, the telephone calls, were in the Oracle Big Data box. I'm using their NoSQL solution, and the graph was extracted in an InfiniteGraph, and then you could explore the graph, and then if you wanted to find out about a person or a place or a credit card or something, that all came out of the Oracle solution. So it's usually you're going to get at least two databases involved in these big systems. The demo I referred to, this was built for a federal police force, an ally. It's not the FBI, something similar in another country. And their problem was that they would see somebody, pick them up and want to issue a warrant to get more information or whatever, but they had to prove there was a connection between the people. And so one simple way was to get their cell phone number and see if they were connected to a known person. Now, maybe they'd seen this person come around the corner from a drug dealer. Maybe they'd walked up, the police officer had walked up to that person, and something had fallen on the floor, and maybe that person didn't know anything about either the drug dealer around the corner or the stuff on the floor. They need to know quite quickly whether there's any connection. And that was taking them minutes to hours to sometimes days to go out 4, 6 or more degrees of freedom trying to find a connection, and they would often have to let somebody go because the query didn't finish in time. We're doing it in seconds to minutes. You can actually see this demonstration on the Objectivity website. Just look for resources and live demos, and you'll find the prescription drug database, the Internet Movie database, and this one. There'll be another one up there soon. You can run them live. If you do go there, just a bit of practical advice, if it doesn't light up straight away, just reload the page. It may be that the server is busy and someone had left it in an untidy fashion or something, and it hasn't yet picked up that particular thread. But it's very easy to use. You go in, you can just choose the number of degrees of separation and the number of paths. I usually start with one of each, and then click the Start Hunt button. And if there's a connection, if these two people have called each other directly, it will tell you in the statistics at the bottom, and it will show you the path. Most times it will come up and say 0. So I usually move it out to about 4 degrees of separation and leave it at one path. That normally produces a result. And I'll crank up the number of paths to 10, so I can see something more like this that's on the screen. And then I'll crank up the degrees of separation to 10 or 11 and get a full picture. So that's a demonstration of it being used. You can adapt this thing to look at things like financial transactions, looking for money laundering, looking for patterns, logistics, customer resource management. It can be used. You can take that demo, download it, and change it for a different domain quite quickly, and start seeing what this thing is all about. And then lastly, I mentioned we like to use our own stuff. So InfiniteGraph uses ObjectivityDB. Graph My Life is a brand new app. It's out in beta. It's currently on Android. It's going through the Apple Store at the moment, so it'll be on iOS as well. And this integrates data from your various social networks, starting at the moment with Facebook and LinkedIn. Obviously, there'll be more soon, and gives you a single picture of what's going on in your life. And one nice part of it is that you can put in a search. Let's see if there's anyone that I know who's in the wine business. And it will go back, not just through the timeline that you see if you look at that person's Facebook profile or their LinkedIn profile. It will go back through those databases and may find things that were first entered by that person 6 months or a few years ago. So we think it's an interesting use of our own technology. We want people to try it. And it's actually running on the mobile device. It's hosted in the cloud, running on the Amazon web service. So it's InfiniteGraph running in the cloud, supporting this little graph demonstration app. So with that, I'll hand back over to Eric and Robin.
All righty. That's a great presentation. I love those graphics, and we'll probably go back to those as we do the Q&A. So, Robin, I'm going to hand you the keys right now to the WebEx. Just click anywhere on that slide and use the down arrow. There you go.
Okay, there's a picture of me looking whatever.
Thoughtful.
Thoughtful, yes, incredibly thoughtful. Okay, I think personally there's something very interesting about graph databases. Well, I'll try and get into this, but if I were to try and classify the number of engines or the different kinds of engines that are out there, I would say there's about 4. It depends on how you choose to classify things. But I would say there's about 4. There's a big table approach to data, which is really, really good for machine-generated data that all goes into one big table, or something that can be compressed into a big table that has a few relationships, but you can drop those and make it a sparse table. There's a relational database, and a relational database is good at set processing as document databases, now called document databases. It used to be called hierarchical databases, but that's a term that the new document databases didn't want to adopt, so they call them document databases. And there's a graph database. And I just thought I'd talk about the distinction between these things. And the first thing is I just like to rub out the word NoSQL, because NoSQL is used to describe pretty much anything that isn't a relational database. So in terms of this graphic on the left, we can see there's complex data, graph data, nested data, OLAP type data, third normal form schema, slow fake star schema, single table. You know, and the NoSQL just spreads quite across that lot, but a NoSQL database can't do all of that. It's particular types of SQL databases that do particular things, which is just me kind of not particularly happy with the word NoSQL. And the point is, what can a given database actually do? So I'm maintaining there's kind of 4 types of engine. There's the big table engine. It doesn't do joins. It doesn't care to do joins, but it processes vast numbers of records that are identical. There's a relational database. It's optimized for data stored in sets, and it does set processing. There's a document database, which is optimized for data stored in hierarchical structures. And there's a graph database, and the graph database is optimized for data stored in graphs or directed graphs, that's networks. And those are very distinct, but in actual fact, if you look at them, some are more distinct than others. A big table database does select and project in terms of its operations, while a relational database does select, project, and join. And if you properly tuned a relational database in the right way, it might, depending upon its architecture, be able to do big table work. You know, and that would depend. You know, we have column stores nowadays because they're much better than row stores for a lot of jobs. So there's different underlying engines between these things, but 1 and 2 are not that far apart. The document database it's not so much select and project anymore. You're kind of doing searches and joins in document databases, and that's what relational database can't do that document database can, and that explains the popularity of products like MongoDB, because they are homed in on basically hierarchical document stores. And then you've got the graph database, and the graph database is really interesting because it's entirely different. You know, when you're putting a query into a graph database, you're actually walking the graph. And when you're walking a graph, you're going from and back to the same table along some kind of edge between vertices. And you're going to store the data to optimize that graph walking, and that's why all the other database engines really perform extraordinarily poorly in trying to walk a graph. It's feasible to build an engine that handles all of these workloads, but it's not feasible to have one that handles them all well. You know, it's possible to have one that would have a language that allowed you to ask any kind of question for any of these workloads and give you an answer. And that's basically because performance is highly dependent on how you physically store the data, and the way that you physically store the data in a graph database is different, and that's why it gets its performance. And this performance, by the way, I would reckon is 2 orders of magnitude to 3 orders of magnitude better than, say, a relational database. In other words, the kind of differences in performance that Leon was talking about, entirely acceptable from what I know of graph databases. Yes, things that took days can come down to minutes or even seconds, because the data is exactly lined up for walking the network. And in my opinion, and I think this is worth just mentioning, the unexploited engines, in the sense that they are not used a lot within the industry right now, and they're not used a lot simply because there have not been a lot of popular products that took, let's say, gained traction and had people using them. But it doesn't mean that there aren't a lot of applications. And this is one of the things that you know, I kind of find curious about graph database. And there's also this, but I'll go into that in a moment. If you look at the way that we do IT, you see that what we actually have is we have networks of servers, and between each server there is a network link of one sort or another, and we have arranged the vertices and the edges in a particular way, and that's what we actually have. And we don't often store data in a convenient manner. So, for instance, if you go into an application on whatever system you use or whatever set of systems you use, when you start doing things, there will be a whole set of logs that will record what it was that you did that come out of the databases, and possibly, you know, there's application logs and so on and so forth. But there isn't anything that traces your path. There isn't any natural store that traces your path. but the trace of your path is an audit trail. And it's really, I mean, try and convince an accountant that an audit trail is a bad thing, and you're going to have a long, long conversation. You know, there are problems that we haven't solved well in IT. One of those is master data management in terms of trying to reconcile different definitions of metadata with each other. And those different definitions exist for very good reasons because they were created to reflect a particular context. That's a graph problem. And that isn't solved easily in terms of getting performance out of walking that graph, the relational database. So there's probably many more areas of applications. I can think of lots of areas of applications in semantic technology that I'm not particularly certain about. But look, we're living in a world where there is well over 250 million servers out there in the web, and they're all firing messages at each other, and there are a whole series of relationships that are going on, you know. And one of the things is that's coming along in the future is this idea that we'll have triple stores, and by being able to investigate the triple stores, we will be able to find semantic information that would otherwise not have been obtainable from the World Wide Web. In other words, we'll be able to get meaning out of the web that we didn't know we could get out of the web until we had this technology. So for me, that's what's exciting about Graph Database. It's not just, you know, the applications that Leon talked about. Some of them we kind of knew that they were going on simply because in one way or another we're in IT, and we hear stories about what the various police services and intelligence services do. And if you read in any great depth about what the British did in the Second World War in order to keep tabs on the Germans, apart from breaking the coded messages, they had databases on cards, and they were following the behavior of individuals in terms of what they did and where they were and why they moved. They were graphing these people, you know? And I think intelligence services have been using graphs possibly since the mathematics of graphs were invented. Anyway, that's all that I've got to say about that. I've got some questions for Leon. So, I mean, here's the first question, and we tend not to think of graph database applications, particularly because we've not had an easy way to search graphs of data. So, my question is, how big is the field of applications, do you think, where a graph engine and the kind of analytics you want to do on that data will actually pay dividends really well? And I know that's a very vague question, but I'm interested in your answer.
No, that's okay, and I think you're right. The whole reason that we built our products, I said, was because we were grappling with problems that had lots of highly interrelated data. In the overall sense, clearly, applications where the graphs are the main thing are fairly specialized. You know, they would be things like the internet, things with the social networking and so on, and engineering design problems and logistics things and so on. But if you look at just about any schema, you'll find that there are generally graphs in there. You look for a many-to-many on an individual entity type, and you're looking at a graph. You look at a one-to-many, you're looking at a tree. So, and what happens in my experience is that solution builders, let's say you're a contractor and you're asked to do something for some large corporation. They give you the problem, they ask for a whole slew of things, and they've got a certain amount of money to spend, and you use the tools you have. And if you're an Oracle partner, you're going to use Oracle if you can. And if there's something nasty in there that you don't want to do, like you don't want to deal with the network of all the bits, corporations and consultants and customers and so on, you only want to go one level, so you can avoid all the joins, your first version of your first deliverable is not going to cope with that problem. You're going to try and get the customer to stop thinking about that problem because you don't have a good solution. And we've seen that over and over and over again, and I've been guilty of it myself in the past. You know, having had one kind of database there and not being allowed to use something else, I've had to just refine the requirements and put everything into phase 2 or phase 3. So that's what actually happens. I think you're absolutely dead on. And there are a lot. We're seeing pragmatically people building proofs of concept, trying our product in just about every industry vertical. Whereas we used to be constrained to a half dozen and I knew my way around all those verticals, there are people coming in from industries that we've never been close to talking to before. So I think there's a lot of potential there. I would say one thing about your 4 engines. I think you're about right. I go even deeper than that and say that in my experience, and I've been building databases since 1969, there are only really 4 ways you can get at data. But that can be a topic of another conversation.
Yeah, well, let's take that offline.
Yeah, and at the moment, the industry is only using 3 of them, which is interesting. At various times we've used a couple of them at a time, but there we are. Anyway.
Well, I mean, you said something that kind of really intrigued me, and I think you were right. I mean, this is my immediate conclusion. I didn't think in any depth because I haven't had much time to let it roll around my head. But, you said virtually all of the data analytics that's going on out there is statistical correlative type of analytics. And graphical analytics is not the same. And the thought immediately occurs to me is, what is the field of graphical analytics? Because I can think of things, like if you take something simple like there's a whole series of customers and a whole series of products. And you can relate, you can relate customers to products. And you can follow graphs between which customers relate to which other customers through which products. Now, I have no idea if that's useful information. I suspect it might be. Have you any idea?
Yeah, sure. And in my early days when I first came over to the United States, the first group of people I worked with wasn't in the intelligence community anymore. It was in engineering design. And so today, if you put all the configuration management data, which used to be a very tricky problem in its own right. I mean, Boeing spent millions and millions trying to get good configuration management systems. They were really the world expert in that area. The systems that they spent millions on building 20 years ago, you could build in half a day now with a graph database. And you could ask questions like, well, why did the left wingtip suddenly fall off? What was the chain of events here? And we had something similar happen under test with a particular material, but it wasn't this material. And you're going to track back through chains, through engineering drawings, through test processes, through manufacturing processes, through suppliers to suppliers, through the way that things were transported. There's a huge graph of information out there, logistical and design and deployment information. And you will probably find there is a connection. Now, some of those connections will be meaningless. But on the other hand, if you find the right one, you're on track to go and find the answer to the problem. And it's very rare these days. In the big systems that we work with, people very rarely put in a query and get what they expected the first time. And I think this is where visual analytics is coming into play. If you give the person the wrong picture of the data, or if the data isn't accessible in the format that suits it, you're not going to get very far.
Yeah, I can imagine that. In your deployments, are you normally stuck next to another engine, or do you sometimes just standing alone? Because it's like, you gave an example of being stuck next to another engine, and my inclination would be, yeah, this looks like you twin it up, and you might be twinning it up with your own object database, but it kind of looks to me like you're twinning it up and you'd replicate one to the other in some way. Is that what you tend to do?
You'd replicate parts of it, and it's probably multiple. So we might grab some stuff out in an Oracle database and a Teradata machine and a Hadoop setup, and some flat Twitter feed or something. And that would all, the relationships be pulled out and put into InfiniteGraph. We recommend to people that since the data is in one place and it's managed properly by the things they already have, they should leave it there, and then just give us a key that we can use to put into the graph, and the stuff that they really want to search on in the connections. And the stuff that goes in the connections may itself come from multiple databases, of course. So it does tend to come from multiple places, and with service-oriented architectures, we really don't care where it comes from. You're going to build a distributed graph database. Parts of the graph may have been built with data from completely different data sets. Part of the graph may be all about design data. Another part of the graph is all about manufacturing data, which is connected to the design data. And then another part is all about test data from individual product instances as they're produced. That's connected back into the manufacturing data and to the design data. But they may have come from 3 completely different data repositories before that graph is loaded into InfiniteGraph.
Yeah, I can imagine that, because a network doesn't have a boundary in the way that a data heap might have a well-defined boundary. So I can imagine you plucking data from lots of different places. And yeah, I can imagine also that you can even find data, you could probably use it for data cleansing, just because,
absolutely.
Yeah, right. You're finding stuff.
Cleansing, versioning of data, provenance, all strong focuses for some application areas. Data provenance is a very big one in the scientific world, the engineering world, and so on. And then the other thing is that you may discover new kinds of relationship as you look at this stuff and want to preserve that so that you don't have to rework the query every time. And so you run a query and you find something and go, oh, that's interesting. I should be labeling this stuff as, not very good for bouncy objects or something. And I'll keep that collection and store it as a graph in its own right. Now, I might come back a week later and rerun the original query and then compare the graph that I get from that query with the graph I produced a week ago to see if it's different. We had a big system built by LexisNexis years ago called AnswerSet that did that for lawyers. It looked at the things that went into a decision on a case. So you could be in court and your pager would go off and it would say, oh, there's a change in the rulings that were used in the OJ case, that are pertinent to your case. So it's very nice to be able to store the results of queries as graphs as well, and also to create new kinds of relationship that you now think are important, and maybe phase out old ones or maintain both.
Okay.
So it's a very flexible mechanism.
Right. Another question, which is just something you mentioned. You say, well, we've got plugins. And I was just curious as to what plugins people write, because I've never messed with one of these. So you have to understand that I understand the theory, but I haven't ever got my hands dirty on anything like this.
No, that's okay. I want a simple one would be to bring up your own favorite visualizer. Okay, so you happen to like Tableau software, let's say, and you run that logistics query I mentioned, and you want to bring it up in a nice Tableau display of some kind. So that's a visualizer plugin. Or there's some computation that you want to run as you go down through the network. I mentioned the logistics one. How much did it cost me to get to this city, to this point on the path between here and New York? Or how much does the aircraft weigh? I start from the top of the aircraft and start accumulating the weight of the individual parts of it. Now, if my computation goes above a certain design limit, I've got to look and see what are the heavy things here? What can I take out of it? So if you're in the financial world, it might be completely different. You might be looking for, let's say the networking world. Okay, so I want to compute the latency and any bandwidth throttling point. I want to know the latency as I go through the equipment in a network. On a particular, if I set up a circuit, a virtual private network from A to B, and I have bandwidth constraints, and I have to provide a certain bandwidth, I have to provide a certain quality of service, and I can't have a latency greater than a certain number. Those are the kind of computations that you would plug into the query.
That's interesting. Am I right in terms of the triple store thing? Is that something you have an interest in?
Oh yeah. We've actually got a sample that you can download that takes RDF and loads it into InfiniteGraph. I would say if the problem you're dealing with fits the RDF OWL model perfectly, and you're happy with Sparkle and so on, you might want to look at a specialized database for that, if that's all you need, because they have very good tools around them and they're optimized for Sparkle. If RDF is a part of the problem, or you're coming from RDF and you want to put it in with some other data and get it into a much bigger graph, a richer graph, then then InfiniteGraph would be the thing to look at. So, but we've had a lot of people load RDF in as one component of the data that they're bringing in.
That'll be interesting to keep tabs on what you do with that. I'm going to have to throw you to the lions in the audience because
okay, no problem.
Now time for their turn.
Okay, good. We do have a whole bunch of great questions, and I wanted to throw one of these earlier slides because thanks to this presentation, I'm starting to wrap my head better around the possibilities here, and it seems to me that the real key to unleashing the power of a graph database has got to be in the identification of valuable edges and nodes, right? In other words, how you load the data into the graph database has a lot to do with how valuable it's going to be to you down the road, right, Leon?
That's right, yes. And then, but if you get it wrong, you can always change it. It's very flexible. So it's pretty straightforward. Because it's a distributed graph database, if you get the placement wrong, let's suppose that I put all the European data in Europe and North American data in North America and so on. It turns out that that's not the way that people query it, and I want to gather it some other way, maybe by product line. That's fine. You can just move it elsewhere, change the placement, as we call it. We call those placement algorithms. But yes, you want to have at least a first, like I did in the example I gave of the people, the events, you know, who called whom and so on.
Right.
It was important to identify which were the nodes and the connections in that one. In real life, it turns out to be pretty simple. A lot of the time, you can see either a direct many-to-many on an entity or two entities connected because it's a many-to-many. You know, the customers and products are connected by orders in the middle. So the order would be a join table in a relational database. In this case, the customer and the product would both be types of node, and the order would just be an edge, a connection.
Yep.
So it usually falls out of the schema pretty quickly.
I see. Okay, good point. All right, let's see. So just diving into some of these questions, one of the attendees writes, regarding visualization of graph database relationships, what are the key problems? And attendee lists like overplotting or identifying the interesting relationships. Can someone discuss what the current research is and what is the next to come from visualization tools showing what is in a graph database?
Oh, that's a really good question, a very wide one. I would recommend looking at the large players out there, the new players like Tableau, and then look at the specialized players like Tom Sawyer, Cambridge Intelligence, see what their visualizations look like. One thing you have to watch out for is that many of these solutions don't scale beyond RAM. So if you get a visualization that's going to take more than RAM, they'll fall over. So that's something you need to try if it's important to you. Nobody can put up a visualization of a trillion node graph in any sensible format. I was talking with someone a few months ago, and we worked out that if you had a display the size of a football pitch, you know, with a pixel 1 millimeter in size, you still can get a trillion nodes on it and the connections between them easily. So you're always abstracting. You're always trying to query to get a smaller set to put on the screen. I am offline. If you email me at leon@objectivity.com, just Leon @objectivity.com, I can point you at some very interesting research at the National Visual Analytics Consortium. And there's also some interesting work at Stanford where we're actually looking at some work based on quantum mechanics.
Okay, great. And here's a really good question. One of the attendees asks, can you see graph databases playing a bigger role in hospital administration, i.e. tracking patients and their relationships to doctors, prescriptions, treatments, billing, et cetera? I have to think that's a big yes, right?
Yes. In fact, watch this space, and we'll be making an announcement in that area fairly soon, I hope.
Okay, great. And I put up this graph because it definitely helped me see into what the graph database is allowing you to do here. And I like the way you just map out 4 different possible pathways, because it's really powerful to be able to include or exclude certain elements, right, to kind of reveal it. And if you could just walk through, like, is this what you do when you're actually typing in a query, or is it more of a graphical user interface, or how do you actually interact with the work here?
Right. We do have a developer's visualizer so that you can debug applications. You probably wouldn't put it in front of a, an end user. But basically, you're writing Java, and you first of all you want to set a policy. I want to go breadth first or depth first. You'll put your inclusions and exclusions. Go down railroads and waterways, but don't worry about anything else. So you put those in, and then you'll name the starting point and end point if there is an end point, and then you'll put in the predicates, conditions that are applied as the thing traverses. So it's going to be a few lines of Java, and then you'll execute it, and what you get back is rather like you would from a select statement. It's called an iterator. It's just an object that you can, every time you call it, it steps to the next one. So you get an iterator back that takes you over the results.
Mm-hmm. Okay, good.
So you write a few lines of code. I actually I have a slide on that somewhere. I'll set that for you, Eric, so you can post it somewhere so that people could get that afterwards, maybe.
Oh, okay. Okay, that sounds good. And we have we've got a bunch of other good questions. So let me just kind of dive into some of these. One of the attendees asks, is the graph database technology mature now, or are we at the place where it's a matter of just building applications to fit into it? What do you think about that?
It is mainly mature. In our case, the engine underneath it is very mature. It's been hardened. It's in millions of deployments in telecom equipment and up in these huge databases. So we have no problems with its scalability or reliability. The Graph API we worked out about 2.5 years ago with the help of the community, and this is an area where it's not mature. Our interface is evolving all the time, and it's a great interface. I would really like to see a standard graph query language for the industry, and we're trying to work with our friends out in the business to get that done. But I think until we have a standard graph query language, we won't see an explosion in usage the way that SQL took off when ODBC came along, for instance.
Interesting.
But each graph database has got good capabilities. We have a very strong set of capabilities. But I just wish there was a standard graph query language today that we could point you at. That's the one weakness, I think, the area that needs work, along with the visualizers. Interesting.
Yeah. Okay, good. I pulled up these slides again because I like the way you very quickly move toward showing how the analysis can point you to some pretty powerful insights. And you have to think that somewhere somebody is leveraging a graph database right now, trying to figure out where our friend Snowden might be, the erstwhile Booz Allen Hamilton contractor, right?
That's got to be true. And one of the systems, the system I first showed you, the example, that's deployed. It was deployed in Iraq, is in Afghanistan, and it's used by analysts on the ground. And so what happens is a fellow out there in the field who typically only has a few years' experience, something green and triangular comes over the hill and something bad happens, they don't know what it is. So they look in the knowledge base, this is an interface to, and there's no green triangular thing. So they enter that. It goes back to a panel of experts back somewhere in the US who look at it and say, yes, we know what that is. And they then enter the metadata about that thing so that we can start collecting more information on those things. And that immediately goes out to this big distributed system out through the defense networks and into the Afghanistan network. And all these fellows out there, living in tents, have got that new knowledge at their fingertips. So it's in use right now for things like that.
Yeah, that's very interesting stuff. And you actually reminded me there's another good question in here. One of the attendees was asking, well, first of all, any lessons learned from XML database, which never took off, but then he goes on to ask about how you can link all these different kinds of databases, and that's really another real key point for a distributed graph database, right, is that you can tap into multiple databases in multiple locations and be able to essentially federate this larger picture of a graph, right?
Yeah, and with XML, if you look at an extreme example, one of the relational database vendors made us all fall about at a conference a couple of years ago when he described how they stored XML in their relational database. And every XML field had a 64-byte tag. Now with InfiniteGraph, we have a 64-bit object ID that represents the node, and we use that object ID as a pointer, for the connection. So it's extremely efficient. So if you've got RDF or XML and you're storing it, and it's maybe a terabyte, 10 terabytes or whatever, it's probably going to take a lot less space in a graph database to store that same information. We've typically found in the past that highly interconnected data gets an overhead of about 200% if you put it in a relational database with indices and join tables, and our overhead's about 20%.
Interesting.
So you actually can cram more data in or keep data longer. No one goes out and buys half a petabyte these days. They buy the petabyte and keep data longer.
Yeah, no, that's right. Well, hey, Robin, I've got a question for you from an attendee who wanted to know, in your mapping of database types, where would you put a multi-dimensional database?
Oh, that's a good question, isn't it?
I put it over there in a refinement of the relationals and the column storage.
Can do it. It depends on how many dimensions you're trapping.
Exactly.
You can do a kind of MOLAP thing, but
that's right.
Yeah, it's a specialist thing, and well caught, whoever that was.
I'd put it in an object database, but
No, I didn't put object database up as a category because of the. It's like, in theory, what can't you put in an object database?
Yeah, exactly. You can put anything. That's what they were designed for.
And so we talked a lot about triple stores, too, in the end, and that is certainly something we're seeing more about these days, especially with discussion of semantics, for example, and ontologies, and you mentioned Sparkle, Leon. I'm curious, one of the attendees wants to know, we hear a lot about triple stores in both document and graph databases. Where do their greatest benefits lie, and what are the trade-offs? Can you speak to that?
Yeah, sure. As far as the... I've got a strange echo there. Am I coming through okay?
No, you sound good.
Okay, I'm sorry. All right, so some local artifacts. As far as the triple stores go, and OWL and Sparkle and so on, they're good if you're dealing with the semantic web. That's what they're designed to do, and it copes with it very well. But there are lots of other highly interrelated systems where, for instance, in the intelligence community, in some scientific applications, it doesn't fit very well. It's not powerful enough, and you need to apply horn logic and so on. And so if you're dealing with something in and around the semantic web, RDF is probably okay, and a graph database will definitely cope with it without any problems. If you need the flexibility and you need extremely fast navigation, then that's where the graph database comes into its own.
Okay, great. Well, folks, we've burned through more than an hour here and tried to get to most of these questions. I think we got to most of them. If not, I posted Leon's email address in the chat window. It's very easy, leon@objectivity.com. But very big thank you to all of our attendees today for some of these great questions. And, of course, a big thank you to our friends at Objectivity. You can see we've got database this month. Cloud is next month, so check us out then. And we do archive all these webcasts, folks. So if you go to InsideAnalysis.com, look under the webcast section, you'll find an area if you navigate for a moment or two to the recent episodes in the briefing room. And I also did a recording of our new show, Inside Analysis, which is just a brief discussion with industry leaders that we'll be posting in a few days with Leon. So check that out in a few days when it comes up. And with that, folks, we're going to end this event. But once again, thank you so much. You can find Leon's email again in the chat window as well as a link to the slides for today. And with that, we will bid you farewell, folks. Thanks again for your time and attention. Take care. Bye-bye.